Music, like... In the name of Allah, the most gracious, the most merciful, praise be to Allah and peace and blessings be upon our Prophet Muhammad, his family, and all his companions. Now to continue, O Allah, there is no ease except what you have made easy, and you make determination and sadness easy, O my Lord, if you wish. We discussed in the previous episodes the details of the line protection scheme and mentioned the methods of signal transmission from one end to the other in both long and short lines. In this episode and the upcoming ones, we will discuss the details of the transformer protection scheme. So stay with us. Fiction screams in every sense, so stay with us. Inspiring. Renaissance. Inspiration. In the electrical power system, crucial elements are protected from faults. Generators have up to 20 protection devices. Transformers follow in importance. Understanding their characteristics and protection methods is essential. Smaller transformers may use fuses, while larger ones have multiple protection types. For transformers under 500 kVA, fuses are used for short-circuit protection. Understanding transformer characteristics and protection methods is crucial. Protection varies by transformer capacity. Smaller transformers use fuses. Larger ones need multiple protections like differential, overcurrent, and earth fault protections. Protection devices are summarized by capacity. Large transformers have protection types like differential, overcurrent, earth fault, standby earth fault, and restricted earth fault. Protection is summarized by transformer capacity. Small transformers, 500 kVA, use fuses for short-circuit protection. No overload protection needed. Medium transformers, up to 500 kVA, use overcurrent and earth fault protection. Critical location transformers, 500 kVA, use restricted earth fault, overcurrent, and mechanical protection. Transformers with 5 MVA or more use differential, restrictive earth fault, overcurrent earth fault, and overflux protection. Here, it is not necessary to use overload protection. Secondly, distribution transformers with medium capacities up to 500 kilovolt amperes, and we use overcurrent protection and earth volt protection with them. Thirdly, distribution transformers installed in important places and with capacities up to more than 500 kilovolt amperes, and we use restricted earth volt protection and overcurrent protection with them, in addition to the Zareli shield as mechanical protection. Fourth, for transformers with capacities of 5 MVA or more, we use several protections. First, differential protection, restrictive earth fault protection, overcurrent protection, and earth fault protection, in addition to overflux protection. In addition to overvoltage and undervoltage protection, as well as overfrequency and underfrequency protection, we also add mechanical protections such as pulse relays, oil temperature protection, winding temperature protection, oil level protection, oil flow protection, and finally, pressure relief protection. Inspiration for a nation's renaissance. And the Owen lever protection, and the Owen lever protection, and then the end of the brass lever protection. Inspiring, mature, and sought. Despite the need to replace fuses after faults leading to time loss, fuses are still widely used in small transformers. They are cheaper than MCCBs and highly reliable in detecting short circuits. Using MCCBs requires downtime for inspection. The main goals of transformer protection are safeguarding against external faults like short circuits and overloads, protecting the connected electrical network, shielding surrounding components, and monitoring operations to minimize risks. Transformer faults vary, with some rare ones like phase-to-phase voltage faults or internal faults between windings, especially in low voltage applications. Finally, if we use an MCCB, we will need some time to keep the transformer out of service, meaning the transformer will be disconnected until technicians and specialists arrive to inspect it before reconnecting it again. The primary purpose of protecting power transformers can be summarized as follows. First, to protect the transformer from external faults such as short circuits, voltage surges, and overloads. Second, to protect the electrical network connected to the transformer at the moment of the fault. Third, to protect the components surrounding the transformer at the moment of the fault. Fourth, to monitor and observe the operation of transformers to minimize risks as much as possible during a fault. As for faults in power transformers, they are varied, and some are rare, such as phase-to-phase voltage faults or faults that occur between the windings of a single phase, which are called internal faults. This type of fault is rare in transformers used in low voltage applications. While their presence increases in the case of transformers connected to high-quality transmission lines, this is due to the exposure of the transformer windings, especially the final ones connected to the network, to impulse voltages with very high values compared to the rated voltage of the transformer. This image illustrates the types of electrical faults that can occur on the transformer. Fault A is called a winding short circuit, meaning a short circuit occurs between two windings. A short circuit means a short circuit occurring between two windings. Fault B occurs within the same phase. Fault C is a short circuit outside. Fault D is an earth fault between windings and ground or neutral. Core faults occur due to eddy currents causing heating, especially at connection bolts. Short circuits within the same phase, and fault C on external conductors are noted. Fault D involves earth faults between windings and ground or neutral. Core faults arise from high eddy currents causing heating, notably at bolts. Such faults in oil transformers heat and break down oil, detectable by Buchholz relay. Tank faults in oil transformers involve oil leaks through body cracks, posing hazards. Key factors affecting fault current in transformers include source strength, grounding method, and fault location. Faults in oil transformers, like those detected by the Buchholz relay, cause oil to heat and break down. Tank faults, where oil leaks through cracks, pose significant hazards. Key factors affecting fault current include source strength, grounding method, and fault location. Transformers face temperature-induced expansion, contraction, vibrations, and localized heating from magnetic flux. External fault currents can also pass through them. Transformers experience effects like temperature changes and vibrations. Overheating may occur due to overloads, harmonics, or poor cooling. A study found the most common transformer faults are in the on-load tap changer, 41%, due to mechanical failures, contact resistance, oil contamination, or overheating. Winding faults are second, 19%, often from insulation breakdown due to moisture, overheating, vibrations, or high voltages. Transformers can also overheat due to overloads or the passage of harmonics through them, in addition to insufficient cooling systems. These effects and others may be the cause of some faults in transformers. One global organization in the field of high-voltage electricity conducted a study showing that the most common faults in transformers occur in the on-load tap changer, accounting for up to 41%. This is due to failures in the moving mechanical parts during operation, increased contact resistance, contamination of the oil, or overheating limits. Following that, winding faults come in second place, accounting for up to 19%. The breakdown of their insulation may be due to moisture inside, overheating, vibrations, or high voltages acting on them. Then, in third place are the faults that occur in the tank and oil, accounting for up to 13%. The lowest percentage of faults in transformers are the core faults, which account for only 3%. This table summarizes the specialization of each protection type according to the type of fault present, and we notice that differential protection is capable of detecting most transformer faults, along with overfluxing and overheating. Notice with me in this protection logic diagram that the electrical protections for distribution transformers are only overcurrent protection and earth fault protection using the 615 relay from ABB, or DONS, the P142 from GE or others. Or others. Mechanical protections include oil temperature, pressure, and level indicators. These detail the circuit breaker, electrical or mechanical, and activate the fail start. For large power transformers, electrical protections are divided into basic protections against internal faults, such as transformer differential protection 87T, high voltage restricted air voltage, and low voltage restricted air voltage. Restricted air voltage is described with symbols 87N or 64N. Low voltage restricted earth fault is also described with the restricted earth fault symbol. Restricted air voltage and low voltage. Restricted earth fault can be described with the symbol. All the symbols are indeed used and correct. As for the backup protections for transformers, they are specific to external faults and those occurring through the transformer. The protections used in this case are high voltage and low voltage overcurrent, represented by the ANSI device code symbol 51. Additionally, there are high voltage and low voltage residual earth voltage protections, represented by the ANSI device code symbol 51N, as well as standby earth voltage, represented by the symbol 51G. In some cases, negative sequence overcurrent protection is added, represented by the symbol 46, to detect load imbalance conditions on the transformer and to identify open conductor cases. This protection can be applied on both the high voltage and low voltage sides. For faults from abnormal operating conditions, there are specific protections for them, such as overvoltage protection 59, undervoltage protection 27, overfrequency protection 810, underfrequency protection 81U, and thermal overload protection 49. The undervoltage protection is 27, and the overfrequency protection is 81O, while the underfrequency protection is 81U in addition to thermal overload protection 49. Overexcitation protection 24 is used, and all previous protections can be implemented through a single relay like RAT620 or RAT670. However, for greater reliability, the RIF615 is used as an auxiliary relay. This avoids relying 100% on one device. F615 protects against low voltage over current and air voltage protection. This diagram shows protections for a 125 MVA transformer stepping down from 132 kV to 33 kV. The RET620 and F615 are used for its protection. The transformer is often symbolized as GTR, meaning grid transformer. 621 of 615 for its protection. This transformer is usually referred to by the symbol GTR, meaning grid transformer. R means grid transformer. The essential protections and the backup high voltage protections present in the RET620 will send a trip signal to the high voltage strict breaker. If the high voltage strict breaker is tripped, it will send a force trip to the low voltage strict breaker. This is only valid in cases of the step-down transformer installed in the substation equipment is usually equipped with a knife switch, meaning that if it trips, it will send a signal to the breaker. They will send a force trip to the high voltage breaker. Transformers have a knife switch to signal breakers if tripped. Backup protections on the low voltage side send trip signals to the low voltage circuit breaker, keeping the high voltage breaker closed. Only standby air volt stage 2 can trip the high voltage breaker by sending a force trip. As for the backup protections on the low voltage side of the step-down transformer, which are usually overcurrent air volt protection or overload protection and are found. Do the RIF615. They typically send a trip signal to the low voltage circuit breaker only, while the high voltage circuit breaker remains closed. The only backup protection that draws its power from the low voltage side and can trip the high voltage circuit breaker is the standby air volt stage 2. The high voltage. The standby earth volt stage 2. The standby earth volt stage 2. If there is a leakage of the transformer current in one direction, it will activate and remove. If it opens and the fault continues, it will then activate to disconnect until we completely remove the fault area. The fault persists, and after the timer, standby port stage 2 will react to disconnect the high voltage legacy breaker until we completely isolate the fault area. Protections trip the circuit breaker without relays. The relay has a close block function. The table shows protections for high and low voltage sides. Protections in the step-down transformer trip high and low voltage breakers, but not vice versa. The CT connection is shown in the diagram, where a single CT serves multiple digital protections for primary and backup. This table shows the distribution of protections for each device, including those that trip the high and low voltage sides. Protections in the step-down transformer that trip the high voltage breaker will also trip the low voltage breaker, but not vice versa. The CT connection to the relay is shown in this diagram, where a single CT is used for digital protections, serving both primary and backup protection. Ideally, CTs for primary and backup protection should be separate. The standby air volt protection draws power from the CT on the transformer's neutral, if ground protection draws power from a single CT on the neutral. The high voltage circuit breaker won't trip with it. The CT connects to the relay as shown in the diagram, where a single CT serves multiple digital protection purposes. The same CT is used for both primary and backup protection. Ideally, CTs for primary and backup protection should be separate. Standby air volt protection draws power from the CT on the transformer's neutral. Ground protection using a single CT on the neutral is symbolized as 51G, while using the vector sum of 3 CTs on the lines is symbolized as 51N, known as residual earth fault. The glass transformer creates a grounding point on the delta side for ground fault current passage. Without a zigzag transformer, ground faults on the delta side circulate within the delta, making detection difficult. Grounding the star side is easier through its neutral. An example of protection for a 132-133 kV transformer shows an independent CT for each protection. Symbol 51G represents the device code, while 51N, powered by the vector sum of 3 CTs, represents ground protection, residual earth fault. The glass transformer creates a grounding point on the delta side. Without a zigzag transformer, a delta side ground fault causes zero sequence current. When a ground fault occurs on the delta side, current circulates within the delta, making detection difficult. Grounding the star side is easier. For a 132-133 kV transformer, each protection has a CT. Devices disconnecting the transformer are lockout relays or tripping relays. 2 lockout relays, 86T1 and 86T2, disconnect the transformer. Each relay operates independently and sends a trip signal. Relays 861 and 862 are on the 132 kV side, sending signals from different sources. The transformer disconnecting devices in this scheme can either be called lockout relays, represented by the symbol 86, or tripping relays, represented by the symbol 94. In this scheme, there are two lockout relays for disconnecting the transformer, which are 86T1 and 86T2. Each device or relay operates from an independent voltage source and sends a trip signal. The tripping coil is also independent, and usually the lockout relays 861 and 862 are installed on the transformer on the 132 kV side, sending a trip signal to the 132 kV from different sources. 86T1 operates when any of the following protections are activated, including protection on both sides, while 86T2 operates when any of the following protections are activated, additional to the transformer. As for 86T2, it operates when any of the following protections are activated, which are in addition to the transformer. 862, standby earth volt on low voltage side. 86T2, count relay triggers with these protections. It activates when the following protection triggers: 5V, low voltage regulators plus buckles relay, connect to A4, reset static changer manually, or the first static changer can be reset manually or electrically through the transformer, ensuring a specialist is present to understand device activation and reset feasibility. This lockout sends signals to the station's control panel and center. In this diagram, all output contacts are parallel. Closing one activates the lockout relay's set coil at terminals A and B. Due to insufficient contacts, another lockout, AT61X, is parallel. Each lockout has a reset coil at terminals C and D. Connecting positive to A and B trips the lockout, while C and D reset it. Notice how all the output contacts are connected in parallel. If one of them closes, it will activate the set coil of the lockout relay with terminals A and B. Due to the insufficient output contacts in a single lockout, another one has been connected in parallel, which is the AT61X. Also notice how each lockout has its own reset coil with terminals C and D. So if positive is connected to A and B, the lockout will trip, and if positive is connected to C and D, the lockout will reset. There are two other devices for transformer protection in this scheme, called tripping relays, which automatically return to their normal state as a self-reset when activated. These are the 9041 and 9042. The 9041 tripping relay operates when any of the following protections are activated: the over-temperature protection for the oil and windings, the 33 kV busbar protection, along with the directional overcurrent and earth volt protection for the 33 kV transformer, will ensure that all protections activating the 86T1 will also activate the 94T1. The protections of 94T1 cannot activate 86T1. Thus, the protection activating the 86T1 can activate the 94T1, while the opposite is not true, as the 86T1 will trip the 132 kV circuit breaker. If the high voltage circuit breaker opens, it must trip the low voltage circuit breaker. However, if the low voltage circuit breaker opens through the 94T1, it cannot open the high voltage circuit breaker. This concerns the step-down transformer. For the 94T2 tripping relay, it operates when any of the following protections are activated. Breaker company. If the high voltage breaker opens, trips the low voltage breaker. The low voltage breaker via 94T1 cannot open the high voltage breaker. This is about the step-down transformer. The 94T2 relay trips with certain protections, sending a trip to the low voltage breaker. Protections include, first, the directional overcurrent and earth volt on the 33 kV side. Notice that in the case of the directional overcurrent and earth volt, it will activate 94T1, while the non-directional overcurrent and earth volt will activate 94T2. The other protections activating the 94T2 tripping relay include standby earth volt stage 1 and protections activating 86T2. They are connected similarly as before. The tripping relay has one coil and terminals A and D. It resets automatically without external signal. One terminal must continuously receive a signal, waiting for another to operate. Why not use it to disconnect? A and D, if positive is connected to D, the relay will set, and when it operates, it will automatically reset without any external positive signal. One of the terminals of the tripping relay needs a constant signal and waits for a signal on the other terminal to operate. What is the reason for not using it to disconnect the lookout or the 860 in the transformer? It receives a signal and waits for a signal on the other terminal to operate. What is the reason for not using it to disconnect lookout or 860, to disconnect low voltage sector breaker H6T in the protection scheme? Lookout or the 860 in transformer, disconnect low voltage breaker H6T, isolate it. The philosophy behind using the 94T for some protections and the 86T for others is that we want to distinguish between faults occurring on the transformer itself and external faults that have passed through the transformer. In the case of internal faults on the transformer, the 86T should be tripped to isolate the two circuit breakers before and after the transformer, and a lockout should be implemented to prevent the circuit breaker from closing again until the specialized team arrives. As for faults that cause an increase in the temperature of the oil and windings, the 94 relay should operate to disconnect only the low voltage circuit breaker connected to the loads. This is because the transformer's temperature rises due to increased loads on it. Therefore, the optimal solution and proper coordination for protection against overheating of the transformer is to isolate only the loads, which effectively resolves the issue. This is because the transformer's temperature will decrease after removing the overload. This means that when the low voltage circuit breaker is opened, the fault will automatically disappear, and there is no need to open the high voltage circuit breaker since it is not related to this issue at all. Here, the 94 tripping relay is used instead of the 86 to disconnect the low voltage circuit breaker because I don't want to implement close block on the low voltage circuit breaker, as the fault is known to be external and not related to the transformer itself. Therefore, after opening the low voltage circuit breaker, the transformer needs some time for the issue to resolve and for things to return to normal. The option of isolating or disconnecting the loads is my last resort, not my first choice, because the temperature rise occurs in several stages, not just one. When the transformer's temperature rises above the normal operating value, we enter the first stage. And at this point, an alarm is sent to reduce the loads and prevent the complete disconnection of the loads. This alarm can be utilized by add a command to operate the cooling fans for the transformer, also known as the cooling system. If the temperature continues to rise and enters stage 2, then the transformer must be completely isolated from the low voltage circuit breaker, and at that point we disconnect all loads at once to prevent the windings from burning or getting damaged. Insulators, as for the usual setup in stations, for operating the fans, is as follows according to this table. If the transformer's temperature rises to 60 degrees Celsius, we then operate half of the fans. However, if it rises to 70 degrees Celsius, we then operate all the fans on the transformer. If the temperature rises to 80 degrees Celsius, we send the alarm to the SCADA system. However, if the oil temperature rises to 90 degrees Celsius, we send the trip signal, which is set to disconnect only the 33 kV. If the temperature rises to 90 degrees Celsius, we send the alarm signal to the SCADA system. However, if the temperature of either one rises to 100 degrees Celsius, we send a trip signal, which is stage 2, to disconnect only the 33 kV circuit breaker. 30 kV, just the breaker. There are two devices for winding temperature, one for high voltage winding temperature and another for medium voltage winding temperature. Note, oil pressure trips the high voltage circuit breaker, while oil temperature or oil level trips the low voltage circuit breaker. It also disconnects the high voltage circuit breaker, while the low voltage only disconnects the low voltage. We are in a state of alert. Now we will move on to another question. What is the reason for using restricted air force protection? Even though transformer differential protection has been implemented to cover the entire transformer area, this is because there are some ground faults on the transformer that are difficult to cover with differential protection. The closer the fault is to the neutral point, the smaller the fault current becomes. In some cases, this current decreases to the point that it may not reach a significant value, especially if the transformer is directly grounded through a high resistance, while the fault current remains large. It means neutral grounding resistor, or NGR, neutral grounding resistor. While the fault current remains large, Even if the fault point is near the coils, a transformer directly grounded without resistance is solidly grounded. The fault current's magnitude depends on the neutral's grounding point, and the voltage at the fault point decreases closer to the neutral. Restricted earth volt protection is accurate and sensitive for such cases. This image shows the fault current. If there's a need for another device to perform this role, restricted earth volt protection has high accuracy and sensitivity in dealing with such cases. Notice in this image that illustrates the value of the fault current for the transformer on the secondary side, represented by the symbol IF, fault current, and the primary side is IS, source current, depending on the distance of the fault location from the neutral point. Grounded systems through MER. About 60% of the winding isn't covered by differential protection. If a fault occurs here, the fault current won't reach the 0.2 baronet setting. Restricted earth volt protection is vital near the neutral. It covers 60% from the neutral. Differential covers 40%. In the recipe to 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 the... Here, the use of restricted earth volt protection has become essential to cover the remaining part of the winding closest to the neutral. In summary, restricted earth volt protection protects approximately 60% of the winding from the neutral point up to 60% of the winding, while differential protection covers the remaining 40%. Up to 60% of the winding is protected, while differential protection covers the remaining 40%. If the transformer's neutral side is solidly grounded, the fault current varies with fault location. The voltage will decrease further from the neutral point, while the fault current is significant. Differential protection covers most windings, even if the fault is far. If the fault is near the neutral point and current is low, neither differential nor restricted earth fault protection detects it. Here, standby earth fault protection is the last defense. Even if the fault is very close to the neutral point, in some fault cases where the fault current is very low, neither the differential protection nor the restricted earth fault protection can detect it. In this situation, we use the last line of defense, which is standby earth fault protection. He is the one. This protection is used as a backup for all ground protections on the secondary side of the transformer and the connected equipment, represented by the bus bar and its connections. Additionally, this protection can be specifically used to protect the resistor used to ground the transformer in exposed systems through the resistor. It is usually used in two stages. If it activates, it will only disconnect the voltage. If the problem persists, it will activate to disconnect. The 33 kV voltage is for the low voltage breaker. If issues persist, it disconnects the circuit. It's fed through the transformer side and operates only if a ground fault occurs within the protected area. It is usually fed through the subject on the transformer side. It cannot distinguish whether the ground fault is inside the transformer itself or outside. Therefore, what distinguishes it the most is that it only operates if a ground fault occurs within the protected area. For this reason, it is called that because its function is limited to detecting ground faults in a specific area only. This means it is considered one of the types of national revival transformers. If a ground fault occurs outside the boundaries of the transformer at point F1, then the relay or restricted earth fault protection should remain stable. However, if a ground fault occurs within the boundaries of the transformer at point F2, then the relay or restricted earth fault protection. If a fault occurs, the principle relies on the vector sum of the three-phase currents 3I0 related to the neutral current. In an external ground fault, the vector sum of the discharger and neutral currents should be 0. Conclusions. The CT ratio for the line CT should match the neutral CT. And the angle between both currents during external ground faults should be 180 degrees. If the fault is internal, the vector sum of the three currents exceeds the restricted air volt current setting, triggering the relay to trip the high voltage circuit breaker. In an external ground fault, discharger and neutral currents cancel out. Line and neutral CTs should match. If internal, three currents exceed the setting and the relay trips. Neutral current's direction stays constant. Only discharger current changes. CT ratios must match. External faults. 180-degree angle, internal faults, vector sum exceeds setting, trips breaker, neutral current direction constant, only discharger direction changes. Restricted air fault protection is like differential protection. Differential current equals vector sum of neutral and three-phase currents, covers one transformer face, hence half differential protection. Independent high and low voltage protections. If either activates, trips high voltage breaker. Neutral current direction unchanged, discharger current changes. Restricted air fault protection, similar to differential protection. Differential current is vector sum of neutral and three-phase currents. Restricted air fault protection covers one transformer face, hence called half differential protection. High and low voltage restricted air fault protection are independent. If either operates, they send a tripping signal to the high voltage breaker. However, restricted air fault protection covers one face of the transformer, which is why it is called half differential protection. This means I have high voltage restricted air fault protection and low voltage restricted air fault protection, and both protections, high voltage restricted air fault and low voltage restricted air fault, are completely independent of each other. If either one operates, they will send a tripping signal to the high voltage restricted breaker. The signal is slow to bless the signal blessing. To prevent minor current differences, we use a stabilizing resistor. This reduces relay voltage to the resistor's voltage drop. Thus, small currents are negligible. The resistor doesn't affect internal faults due to high fault current and no opposing current. This is called restricted air fault protection. It can be installed for similar reasons as before. The effect of these small currents becomes negligible, while the added resistor has no effect in the case of internal faults due to the high value of the fault current. This is called restricted air fault protection. Installation depends on the case. No need for additional resistors. When we add this resistor in series with the relay, we refer to this protection as restricted air fault protection. If we say that it can be installed for the same reasons we mentioned in the previous episode, it means that we can install one only in certain cases, while in others, we install each one independently. Since there is this type of protection, it also means that we don't need to install resistors or connect each one to a phase independently. In this case, we install only one, while in that case, we install each one independently. Since there is this type of protection, it also means that we don't need install resistors or anything else. Each one is connected to a phase independently, and since there is this type, it means that there is also a fault. And we don't need to install resistors, nor even a metering device. In this case, each one can be connected to the relay separately, and using calculations and comparisons internally, and rely on the idea of curves as explained previously. It has recently spread in the store. The installation of a digital relay and the placement of high resistors in series with it simulate high impedance, whether for restricted air fault protection or differential protection. This image shows the installation method for high impedance restricted air fault protection with a digital relay, while the other image shows the installation of high impedance differential protection with a digital relay. Can the delta side of the transformer or the ungrounded star side be used with no neutral present? Use ground leakage protection devices operating on voltage rather than current, because current-based devices don't function properly during a ground fault in systems isolated from the ground due to low fault current. Advantage: voltage-based devices have the vector sum of the three-phase voltages normally equal to 0. If a phase ground fault occurs, the voltage on that phase will be 0, making the vector sum non-zero. This broken delta method is ineffective for specific area fault detection. Note the difference between the broken delta connection and the open delta. Ineffective detecting ground faults in specific areas. Note the difference: broken delta, windings form a delta, two ends open for relay on residual voltage. Open delta, two phases connect in series and star. Broken delta and open delta. The broken delta is the secondary windings in delta with two ends open for residual voltage relay. In open delta, two phases connect in series. In star configuration, voltage becomes 1 now SQRT3 of delta voltage. Thus, open delta provides 57.7% of traditional transformer capacity. Approximating P1 in open delta protects against voltage spikes and prevents secondary winding damage during faults or load changes due to capacitive and inductive effects. Another goal is to create a fault current path and activate protection for faults between secondary winding terminal and ground. Some stations use a zigzag transformer or parallel delta to create a true neutral. A grounding resistor connects through this neutral from the zigzag transformer to increase ground resistance. It protects against voltage spikes on the secondary winding. It provides a path for fault currents and activates protection if a fault occurs between the secondary winding and ground. A zigzag transformer or parallel delta connection creates a neutral point. A grounding, protect faults between secondary terminal and ground. Stations use zigzag transformer or parallel delta for neutral point. Grounding resistor through neutral increases resistance. CTs on neutral for air fault protection. Zigzag protection via CT before it with suitable CT ratio. Signals relay or CT after for restoration. At the same time, we place CTs on this neutral for the purpose of using them for standby air fault and restricted air fault protection. As for the protection of the zigzag itself, we can install overcurrent and air fault protection by placing a CT before it with a low and suitable CT ratio that aligns with the auxiliary transformer. But if it functions effectively, it sends a signal to the specific relay. Or we can protect the zigzag area by installing a CT after it and connecting it to the system. In this particular case, it should be capable of restoring the system, not just providing protection. Additionally, it is important to ensure that all components are working in harmony. And it's not just the truisms. Can a national relay operate in the event of a cut in one of the phases? It will be considered. Ensuring stability. 2 healthy currents equal the return from the neutral, keeping the difference 0. Can restricted air fault protection operate during phase-to-phase or 3-phase faults, even with incorrect zero-sequence currents? Firstly, zero-sequence currents should not appear in such cases. And the governorate of the governorate of the governorate, the sum of the 2 healthy currents equals the amount returning from the neutral, keeping their difference 0. Can restricted air fault protection work during a phase-to-phase or symmetrical 3-phase fault? Zero-sequence currents shouldn't appear in these cases. Asymmetry in current waveforms across phases occurs due to rapidly emerging DC components at the fault moment, caused by differences in voltage waveform angles, known as the voltage incident angle. There's a delay in the circuit breaker cutting current across phases until each waveform passes the 0 point. Their appearance can be due to several reasons. First, asymmetry in current waveforms due to decreasing DC components happens rapidly at the fault. This is due to the difference in voltage waveforms angle at fault. Secondly, delay in circuit breaker cutting current until 0 crossing. This means the sum of currents at fault won't equal 0, causing brief current appearance. Variation in circuit breaker timing due to mechanical fault is circuit breaker pull discrepancy, worsening zero-sequence current. Heavy phase fault can cause false zero-sequence current, or zero-sequence currents may appear symmetrically but don't produce neutral current. The sum of currents at the fault moment won't be 0, causing a brief current less than 1 cycle. Circuit breaker pull discrepancy due to timing variations in breaker operations across phases exacerbates zero-sequence current. A heavy phase-to-phase fault can cause false zero-sequence current, and zero-sequence currents may appear symmetrically but don't produce neutral current. When testing without unbalanced current, the relay won't detect a fault. The relay needs unbalanced current across phases, at least 3% of the relay. Zero-sequence current can appear with a phase fault, causing false zero-sequence current. Some zero-sequence currents may appear in symmetrical conditions, but don't produce neutral current. When testing current to simulate imbalance without unbalanced current, the relay won't detect a fault. The relay needs unbalanced current across the 3 phases, not less than 3% of its rating. So, when testing and injecting current just to simulate imbalance without the presence of unbalanced current, the relay won't detect any fault. Therefore, the relay requires the presence of unbalanced current across the 3 phases, which should not be less than 3% of the relay's rating. 100 of IBS. But 100 of IBS. Current is like a haze. Current, it is met by a neutral current of no less than 50% of the minimum sensitivity differential current. Until it is determined whether this is a fault condition or not, knowing that the presence of a neutral current is sufficient for the relay to operate regardless of the presence of a residual current. But the presence of a residual current requires the presence of a neutral current for the relay to operate, and this amount will suffice in today's lecture. Join us in the next episode where we will explain the details of connecting the directional groups of transformers, preparing to understand their impact on the differential protection of transformers. Glory be to you, O Allah, and praise be to you. We bear witness that there is no deity but you. We seek your forgiveness and turn to you. We hope to see you again.